So let's model more functions, more quadratic functions, but then look at some things and write them in vertex form because it's going to help us find the vertex, or maybe we'll write it in vertex form because we have the vertex. We'll see what happens. So standard form of a quadratic function is ax squared plus bx plus c. That tells us very little about the graph. It just has a graph it. The benefit of having something in vertex form is that it looks like this. So we have a, and then we have x minus h squared plus k. And a is just, it's just your, like a growth rate type thing. And then h and k are your vertex. So that makes it to where it's easy to find your vertex from the equation. So that'd be great if I know how to do that on Desmos, but I don't. So we're going to go with what we have. And we're going to put this data into Desmos. We're going to use the graphing feature to look at the scatter plot and figure out, is it quadratic, is it not, and why is this going on? So if we look at the data, it's this one. We have this little wonky hill type thing where it goes up and then down and then back up and then back down. So maybe not a great quadratic regression. Maybe it is. It does go up and then back down. So one reason, and it wants us to point these things out. So let's practice writing these answers. Provide one reason why a quadratic equation might be an appropriate model and one why it's not. So it may, so might be quadratic because the graph, it goes up and then down. We call that increases and decreases. Might not because there's not a clear maximum, right? It doesn't actually go up to a point. So it doesn't look like it has a clear max. All right, and that's just one reason. You probably come up with a couple. Determine a quadratic regression equation for the data set. Then analyze the residual plot. Does the residual suggest that a quadratic model is appropriate? So let's look at this information. We have this problem. Let's go to the quadratic regression. Okay, the statistics here suggest, yeah, that's a pretty good quadratic regression. It's not linear, right? That's not a good number. It's not close enough to 1, and it's not exponential. Again, so that doesn't really even make sense if you look at it. So we've got this nice curve. There's clearly going to be some, discrepancies here. And then if we plot the residual, oh, look, that looks kind of patterned, right? It looks like it's going up and then down and then up and then down pretty similarly. So maybe not. So the residual doesn't suggest that it should be quadratic. We are, however, going to write the answers to the problem. So why, regardless of what we think it should be, the regression, oh no, I should have written this down. We've got negative 0.008 x squared. And now I'm going to have to look back at the graph. Doesn't take a little bit more time. 0.7396, 16.03. 7396. 16.03. This has x. I think they're both added. I'm going to check one more time. Yes. Okay. And the residual suggests not quadratic because it shows a pattern. Fun fact though, they don't care. They say, what is the maximum value? And what does it mean in the context of this problem? how does it relate to the graph of the regression equation? So let's look. Let's go over here. Great thing about Desmos is that they point out that maximum for you. So it's 44.6841 or 44.641 and 32.538. So let's write that down. The maximum value, just like I said. So this means that a car traveling 44.642 miles per hour is getting 32.539 miles per gallon. And I'm able to know that because I read ahead, right? I actually read the situation. So if you couldn't get that just by knowing it off the top of your head because you're not a mind reader, then you would read the problem, right? We're talking about fuel efficiency given a particular speed. So if your speed, as your speed increases, it looks like your mileage increases, but then it goes down. Right? Because if you're going too fast, you're using too much fuel to run your car. So that happens, right? A lot of times the speed limit is probably around a good mileage to go to be able to get the most out of your gas that you put into your car. So it's pretty interesting. And then if this is the data set that the FHA used to estimate that the most fuel efficient speed for driving a mid-sized car is 55 miles per hour, how did they come to that conclusion? Well, if we look at the 55 miles per hour range, just given this data, right, we know that based on the information here, 32.4 is the best mileage that we're going to get. Just from the data, maybe not from the regression, but from the actual data. So they're guessing they're 55 because they're maybe not looking at a regression and looking at the quadratic function. They're just looking at the numbers that are here, and they guess, oh, okay, 55. That's where it's hitting the max based on the table. So that's probably it, right? And we can also see that after 55 miles per hour, your mileage goes down. So that would be the answer to that question. You need to write down what I just said as best as you can. Your teacher will be checking to make sure that you actually listened to that answer. If you didn't listen to it, you won't get to write it down. Oops. Make sure you write it down for full credit.